Hi everyone, Tina here, and today I'd like to talk about proof by contradiction. This is a topic that's usually taught in year 2 of the A-level course. I have made a video on A-level proof in year 1, so I'd recommend you watch that one first if you haven't already. I'll go through some examples of proof by contradiction, and I'll show you a template that I use as I do this. Example 1. Prove by contradiction that if x squared is odd, then x must be odd. I've put my template on the side here, so there are 4 steps in the template. Step 1 is to always start by saying assume the statement is false, and then i.e., and this will be question specific, but in this case we could say something like i.e., if x squared is odd, there exists an x that is even. That's step 1 complete. Step 2 is algebra, again question specific, but you follow on from your assumption. So in our assumption here, we've said if x squared is odd, then there exists an x that is even. So because we've said there exists an x that is even, we can say x equals 2n. We can then investigate this a bit more. So we're talking about x squared. Let's see what happens if we square this. We get 4n squared. This, in fact, is even because you could take out a factor of 2 and have 2n squared inside the brackets and say that's even. That's step 2 complete, because step 3 is where you get to say this is a contradiction. It's a contradiction because in our assumption we said if x squared is odd. However, when we investigated using the algebra, we found out that x squared is in fact even. Step 3 is literally just writing this is a contradiction. And then finally, step 4 is our conclusion, which you can learn and then use across other proof by contradiction questions. The conclusion I prefer is something like, therefore, assumption is wrong and original statement is true. And that's it, 4 steps. Example 2. Now I've put learn here because this kind of question can come up quite often, but the algebra in step 2 is quite specific. So it's probably easier that you memorize what to do so that you don't get stressed out in an exam if this question comes up. In the exam, this root 3 could be any surd. The algebra I'm going to show you will apply no matter what the number is. Step 1 is the same. So we're going to start by saying assume the statement is false. In this case, we're going to say i.e. root 3 is in fact rational rather than irrational. Now, because we're saying that root 3 is rational, that means we can write it as a fraction by the definition of what a rational number is. We're going to extend this to say where a and b are integers and have no common factors. In other words, what we're saying is that a over b is a fraction in its simplest form. This might seem a bit random at this stage, but you'll see why we need to say this in step 2. For now, step 1 complete. Step 2 is the algebra. So we start with root 3 equals a over b from the assumption. We could square both sides to get this. And then based off this, we can say that means a squared must be equal to 3b squared. This implies that a squared is a multiple of 3 because a squared is 3 times something. This in turn implies that a itself is a multiple of 3, and therefore we could write a as 3n. We can now take the fact that a is equal to 3n and sub it in here, so we can say 3n squared equals 3b squared. If we expand this out, we get this, and if we divide by 3, we get this. This implies that b squared is also a multiple of 3, which in turn implies that b is also a multiple of 3. Step 2 complete because now we can say this is a contradiction. It's a contradiction because we explicitly stated that a and b have no common factors, yet in the algebra step we found out that both a and b are a multiple of 3. So there is a common factor of 3 according to the algebra. Step 3 complete. Final step, conclusion. Therefore, assumption is wrong and original statement is true. And that's it. Example 3. I'd also recommend that you learn this one. Prove by contradiction that there are infinitely many prime numbers. Let's make a start by assuming the statement is false, i.e. there are a finite number of prime numbers. Step 2. If we're assuming that there are a finite number of prime numbers, then we can say let x equal product of all primes. In other words, we're going to say x equals all of the finite prime numbers that we mentioned multiplied together. After that, we're going to say let y be equal to x plus 1. If we use our algebra from the step before, that means y is going to be equal to all the prime numbers times together then a random +1 on the end. We've done this so that we can say y has no prime factors, p1 to pn, because there would always be a remainder of 1. Why is this important? Well, step 2 is complete, but it's important because this leads to our contradiction statement. This is a contradiction because, in this case, either y is prime itself, which is why it didn't have any prime factors p1 to pn, but that's a contradiction because that means y was not in the original finite list of prime numbers. If y isn't prime itself, then the fact that there's a remainder of 1 means it must have a prime factor that was not in the original finite list either. Either way, this is a contradiction to our assumption. The fact that we've contradicted our assumption means we can write our conclusion. Therefore, assumption is wrong and original statement is true. And that's it. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else that you think might find it helpful. Thanks, and see you next time.